In the previous video, we considered the effect of the initial momentum on the force of impact of a ball when it hits you. In this one, we want to take a look at how does the material of that the ball is made of affect the force of impact.
During the impact with the ball, you can say that the average force is just the change in momentum divided by the change in time. Since the force is the derivative of the momentum, you can define the average force, which will be the delta p divided by the delta t. Just like we define average acceleration for a velocity versus time plot by taking delta v over delta t. So the equation that we have for the average force that the ball put on the leg of the person, we can use this, and it's going to depend on the final momentum and the initial momentum and the collision time, right? The difference between the final momentum with the initial momentum divided by the collision time, that will give you the average force of impact, right? So this is where the material is going to show up. One of the places where it's going to show up is that if the ball is made of a material that doesn't bounce a lot, then your P final is going to be close to 0. The ball hits you and it doesn't bounce back, right? It just hits and falls, like a ball made of clay, for example, would do something like that. So that would be one place where the material shows up. Two balls sent with the same initial momentum, right? And suppose that they have the same collision time, then the ball that has the smallest final momentum will be the one that delivers the least force, right? Two balls that look identical have the same mass. They're made of two different materials. This one has an elastic collision with the table. This one has an inelastic collision with the table, right? So the question regarding this is, which one of these two puts more force on the table when it hits it? So let's look at this situation. The elastic one comes down with some velocity, right? It bounces with pretty much the same speed, opposite direction, but about the same speed, right? The inelastic one comes down with the same velocity as the other one, but it doesn't bounce. Its final velocity is 0, right? So why don't we look at the change in momentum, experienced by this ball. So the final momentum is mv. Let's say that the magnitude of the speed is v, right? So final momentum is mv. It came down with minus mv. Minus is, remember, it's a vector, so you have to deal with the different directions. So what's the change in momentum that the elastic collision, that the elastic ball experienced? Is the final momentum minus the initial momentum, right? So the final is mv, the initial is minus mv. Okay, so what is that equal to? That's right, 2mv, right? So the ball that bounced experienced a change in momentum of 2mv because it had minus mv to start with, and it ended up with plus mv. You start with a debt of $1,000, and after 1 month you have $1,000 in the bank. So your change in money, you would receive an inflow of $2,000, right? So the same situation here. You had minus mv, later you have mv. What's the change? You had mv to bring it to stop, and another mv to make it go up. So that's 2 mvs. So for the elastic one, you can do the same. So because the change in momentum is 2 mv, then the average force acting on that ball would be the change in momentum divided by the collision time, how much time the collision lasted. So 2 mv divided by the collision time. That's going to be the average force experienced by the table. Let's do the same exercise for the inelastic one. We know that the initial momentum is going to be the same as before, minus mv, and that the final is going to be 0. So what's the change in momentum? Final, 0, minus initial, and the initial is minus mv, so minus minus, you get mv. So the average force is going to be the change in momentum, mv, divided by the collision time. So if we're assuming that these two balls are having the same collision time with the table, right, then clearly this one, the elastic collision, delivers more of a punch, twice as much as the inelastic one. One of the reasons why it sounds counterintuitive It's because the inelastic collision makes a lot of noise. So it leads you to believe that the force was bigger. This one doesn't sound as loud, right? That's because this one is wasting a lot of the energy, is going in terms of sound. This one is not using that much energy in terms of sound. Most of the energy is going back, right? It's staying with the ball. So like I said, if the collision times are the same, then the average force delivered by the elastic one should be bigger than the average force delivered by the inelastic collision. So the material is going to influence the final momentum. We just saw that. And that, of course, is going to have an effect on the average force. But the material is also going to influence the collision time. Yeah? Because a very squishy ball is going to have a longer collision time than a ball that is hard, right? You can imagine a very squishy ball coming down, touching the table, getting compressed, and this whole process taking a long time, right? Whereas if the ball is very rigid, then that happens a lot quicker, right? So the rigidity of the material is also going to affect the collision time, which shows up in the denominator of the average force. So a longer collision time means a lower average force, right? So suppose that you throw an egg to a wall. The egg is going to come to a stop, obviously, right? But the collision time between the egg, in that collision, the collision time is going to be quick, right? So that means that the force, the average force that the wall is going to have to put on the egg is going to be bigger than the egg can stand, and the egg is going to break. I'm already showing you the answer to the question that I was asking you, going to ask you. How would I throw the egg? How would I slow down the motion of that egg so that the egg doesn't break? I want to bring that egg from the same initial momentum that it had when it hit the wall, but I want to bring it to a stop without breaking it.
You have to change the wall.
So the material is going to have to be different, right? And you're going to need to have a lot of give in the material that is colliding with the egg so that you can extend the collision time, right? If you're able to extend that collision time, instead of making it milliseconds, you make it, tenths of a second, right? Then you're reducing the amount of force by a lot, okay? So how do you apply the same idea? You're the egg and you're in a car. How do you apply the same idea to keep you safe in a car, in a crash? Airbags, right? So what the airbag is going to do is going to try to extend that collision time. If there's no airbag, when the car stops, say that you hit a wall or another car, when the car stops, you're going to want to continue moving because of Newton's first law, right? So you have a lot of inertia. So maybe your body is attached to, hopefully is attached with the seat belt, right? But your head is not attached to the seat with the seat belt. So your head and part of your torso is going to want to go forward, right? So the car stops and you continue to move. So there's a amount of time after the car has stopped that you're still moving, right? And then something's going to have to stop you. It could be the windshield, it could be the steering wheel, right? And that collision is going to be a collision between two hard materials, right? The collision time is going to be short. So the force involved is going to be pretty big, and that can break your head, right? Just like a collision with a wall will break the egg. So what is the airbag going to do? As soon as it senses that the car is stopping suddenly, it inflates in a very short amount of time, very, very quickly. Okay? So when the car stops and you still have this forward motion, you're already in contact with the airbag. So the airbag is already putting a force to slow you down. And that force is acting over a long distance here, So it has a lot of time to slow down the motion of your torso. Okay? So that means the collision time is long, and the force required to slow you is therefore smaller, much smaller than if you just stop by.
Why sometimes the airbag kill people?
If it's a baby, for example, that's why they don't recommend putting babies in the front seats, right? When the airbag has to inflate very, very quickly, right? Because, you have the collision time is going to be very short between the car and the wall. So these things inflate very violently. In fact, if you are next to it when the bag inflates, it's going to push you really hard, right? So the idea is that the bag is going to inflate before you, it's not going to hit you, and then you're going to move forward and encounter this pillow that's already there, right? But if it inflates, for example, too late, right? If you're already moving forward and then the airbag suddenly comes out, you might be halfway here and the bag is going to inflate all the way here, so that's going to hit you and push you back, right? So that can break your neck or something like that. So those things are obviously dangerous. But if they inflate properly, they save your life. The shape of the ball, in terms of how much force and how much pain it inflicts, right? The shape is obviously important. If I make a ball with spikes, that obviously hurts more than a ball without the spikes, just in the same way that a high-heeled person stepping on you hurts a lot more than the same person stepping on with tennis shoes, right? So the area of contact is important. So if the ball gets deformed a lot with the collision, in the collision with you, then the area of impact is bigger, and the pressure applied, which is the force divided by the area, we'll talk about that when we talk about fluids, is smaller in this case than in this case, right? Your pain receptors are not just going to react to the force, but to the force per unit area, right? That's why a little bit of force applied with your finger doesn't hurt you. The same amount of force applied with a needle hurts because it penetrates the skin, right? So the force per unit area is important when talking about the sensation of pain. So the shape, obviously, then it's another factor there. So what if you wanted to pick the most painful ball to take revenge of that guy who hit you before? How would you pick that ball? Baseball. Okay, so what kind of properties do you want? Baseball sounds like a pretty good one. Yeah. What kind of properties do you want in that ball?
It has to be a hard material on a small surface area. Harder ball.
So as small as possible, but heavy also, right? So big, very dense ball, right? Elastic in general should be better than inelastic because it delivers twice the punch, right? The problem with elastic is that it might be too squishy also. So you want to pick, if you want to go with elastic, make sure that it's a very hard elastic material, right? So the elastic part was, remember, because the delta P was a maximum when it's elastic, right? You want to choose a hard one because the hard one minimizes the contact area, right? And also the hard one minimizes the collision time, right? The soft one has this long collision time, right? The hard one just bounces back immediately. Dense, what we said before, right? You can make a dense ball heavy but small, and then the area of impact is smaller. So this is what we talked about last class, and today this is sort of like a map of concepts here, right? We started by the discussion of the game, then the question of which ball is going to hurt the most. We talked about different properties that determine that: mass, velocity, material, and shape. The mass and velocity led us to talk about the concept of momentum, right? Then we connected the concept of momentum with the force. We're interested in how much force, right, the ball is going to impart. The connection between these two concepts is through this. The integral of the force is the impulse, and impulse, the net impulse, is going to be equal to the changing momentum of the system, right? The material, from the material we looked at the average force, right, which is changing momentum. It's coming from here, right? Changing momentum divided by the collision time. So the material shows up in two places in this equation: in the momentum, final momentum, and in the collision time, right? The final momentum, difference there, elastic and inelastic collisions have different final momentums, right? The collision time has to do with also how whether the object gets deformed or not, right? And that has applications in terms of saving an egg thrown towards a ball, towards a wall, or car, airbag, and stuff like that. Talked about the shape because of the contact area. Okay, so that's pretty much what we've talked about so far.